Hello everyone. Our project title is Switched Capacitor Based Step Up Single Phase 9 Level Inverter. Contents are objectives, introduction, existing method, disadvantages, proposed method, simulation results, advantages, applications, conclusion, and references. Objectives: in order to overcome the problem of distortion in the output voltage waveform caused due to the presence of harmonics, to study and simulate a single phase 9 level voltage source inverter, and to understand and implement pulse width modulation for minimization of filtering requirements. Introduction: nowadays, the depletion of conventional resources have increased the interest in renewable energy sources. Photovoltaic is the best one of renewable energy sources because it causes no pollution, noise less, and have low maintenance cost. Accordingly, suitable power electronic converters are needed to produce a high quality power from PV arrays. Multi-level inverters are an appropriate method for medium and high voltage power applications due to its ability to produce high quality AC output current. They can produce highly sinusoidal voltage at medium or high voltage range by using many low voltage reliable power devices. With multi-level converters, filters can be reduced. The proposed configuration uses switched capacitors as an alternate DC power supplies to produce a sinusoidal output voltage waveform. A straightforward switching control strategy is implemented using a logic control circuit to ensure balanced capacitor voltage relying on pulse width modulation. Existing method. There are three types of multi-level inverters: diode clamped multi-level inverter, flying capacitor multi-level inverter, and cascadal multi-level inverter. This is the block diagram of diode clamped multi-level inverter. In this, the main concept of this inverter is to use diodes and provides the multiple voltage levels through the different phases to the capacitor banks which are connected in series. A diode transfers a limited amount of voltage, thereby reducing the stress on other electrical devices. The maximum output voltage is half of the input DC voltage. This is the main drawback of the diode clamped inverter. This problem can be solved by increasing the switches, capacitors, and diodes. Due to the capacitor balancing issues, these are limited to the three levels. This type of inverters provides high efficiency because of the fundamental frequency used for all the switching devices, and it is simple method of the back-to-back power transfer systems. And this is the block diagram of flying capacitor multi-level inverter. The main concept of this inverter is to use capacitors. It is of a series connection of capacitor clamped switching cells. The capacitors transfers the limited amount of voltage to electrical devices. In this inverter, switching states are like in the diode clamped inverter only. Clamping diodes are not required in this type of multi-level inverters. The output is half of the input DC voltage. It is the drawback of the flying capacitors of multi-level inverter. It also has a switching redundancy within the phase to balance the flying capacitors. It can control both the active and reactive power flow. But due to the high frequency switching losses will take place. And this is the 5-level cascaded H-bridge multi-level inverter. The figure shows that 5-level cascaded H-bridge multi-level inverter. The converter consists of two series connected H-bridge cells which are fed by independent voltage sources. The outputs of the H-bridge cells are connected in series such that the synthesized voltage waveform is the sum of the individual cell output voltage is given by V is equal to V1 plus V2. Now the disadvantages of existing methods are: first, the diode clamped multi-level inverter. DC level will discharge when control and monitoring are not precise. Number of clamping diodes increases with the increase of each level. Static wear compensation. And for flying capacitor multi-level inverters, voltage control is difficult for all the capacitors. Complex startup, poor switching efficiency. Capacitors are expensive than diodes. And for cascaded H-bridge multi-level inverters, every H-bridge needs a separate DC source. Due to large number of sources, applications are limited. And this is the block diagram of proposed method. And the block diagram consists of a single DC source, 8 switches, 2 capacitors, and 2 diodes. The capacitors C1 and C2 are used alternatively with the DC supply to produce a higher output voltage. By sequential and systematic turning on and off of the switches, the capacitor C1 is charged equal to the supply voltage and C2 is charged up to double the value of input voltage. In proposed method, the implementation of 9-level inverters so as to overcome the limitations associated with the use of low-level inverters, increasing the inverter levels will result in an output waveform which is closer to the sinusoidal waveform. The proposed configuration uses switched capacitors as an alternate DC power supplies to produce a sinusoidal output voltage waveform. Therefore, only one DC source is needed. Instead of using a traditional power semiconductor devices like transistors or thyristors, switched capacitor inverters utilizes capacitors and switches to dynamically alter the voltage levels and generate the desired waveform. And next, this is the switching logic states and capacitor states. Here we use multi-carrier pulse width modulation is used with the number of carriers proportional to the levels number in output voltage, and therefore here we see that carriers number will be n minus 1. Accordingly, 8 carriers have the same frequency and amplitude but with different offset voltage are used for the proposed topology. The carriers VCR1 to VCR8 are compared to a reference sine wave. And these are the specifications we use. Input DC source 100 volts, output frequency 50 Hz, R load 400 ohms, RL load 400 ohms and 150 megahertz, C1 330 microfarads and capacitor C2 660 microfarads. For switching frequency 100 Hz and 5000 Hz. And this is the simulation diagram for output voltage and capacitors voltage for switching frequency 100 Hz. And here we see that the capacitor's voltage varies around 100 volts for C1, and for capacitor C2's voltage varies around 200 volts, that equals to twice the supply voltage. The capacitor voltages self-balance without the use of any balancing control scheme. And this for output and capacitor's voltage at switching frequency 5000 Hz. It is evident that the generated output voltage consists of 9 levels of voltage with a maximum peak value of 4. And this is for the inverter's output voltage and current for load change. Firstly, the resistive load is equal to 400 ohms that is connected to the load, then change it to no load case. Finally, RL load is equal to 400 ohms plus 150 megahertz that is connected to the load for a DC source voltage of 100 volts, and switching frequency is equal to 5000 Hz. Here we see that the time for output current 0.06 to 0.12, this is for R load, and 0.12 to 0.16 for no load, and 0.16 to 0.2 for RL load. In RL load, we can slightly see that sinusoidal voltage, and this is for the inverter voltage and current are analyzed for different modulation index of modulation indexes is equal to 0.8, 0.9 and 1. At this condition, inverter's voltage levels are maintained. And this is for load voltage and current for another condition of modulation index 0.4, 0.7 and 1. The inverter's voltage levels are changed to 5, 7 and 9 levels for modulation indexes 0.4, 0.7 and 1 respectively. Consequently, load current value is changed. And now we see the advantages. The advantages are increased output voltage levels, reduced voltage stress on power devices, compact design, greater flexibility, improved efficiency, enhanced output voltage waveform. And next, applications. The applications are renewable energy systems, electric vehicles, industrial motor drives, microgrid systems, uninterruptible power supplies. And finally, the conclusion is this innovative design combines the benefits of quadruple boosting and switched capacitor techniques to achieve a 9-level output with fewer components, leading to a more compact and cost-effective solution. The reduced component count not only simplifies the manufacturing process but also enhances the overall reliability of the inverter. Thank you.